Hi everybody. This is a very nice exercise. We're going to just begin this exercise and then I got a couple of assignments to go with it. We're finding links in and around circles. And this is just going to be some notes. But consider this. With chords AC and BD intersecting each other, they happen to intersect at point E. Introduce segments AD and AB and CD. Let me do just that. Let's take a look at what happens when we do that. Talks about similar triangles. In class, I'm sure I'll stop that video and ask people why those triangles will be similar. You people at home should be thinking about that too. I would be thinking that this angle at A is going to be congruent with that angle at D. Why do I think so? Because those two inscribed angles cut the same arc. The vertical angles are congruent, and that two pairs of angles being congruent is enough for me. But the truth is also, it's pretty clear to see that the angle at B would be congruent to the angle at C, because those two inscribed angles cut the same arc. So yeah, we do have similar triangles, don't we? Make a statement about it. I'll call the one on the left triangle ABE. Triangle ABE. And you ought to name the other one carefully. And you would be thinking that the angle at A goes with the angle at D. So we got to put D first. And I think it's important that we name these well so we can get these proportions right. So that was ABE, so DCE. How'd you get those to be those triangles to be similar anyway? Yeah, that's the common way, angle. Meaning the two angles of one match the two angles of another guarantees the triangles are similar. And if they're similar, the big deal is we're going to write a proportion. Set a proportion that involves AE, EC, BE, and DE. Now those are just the lengths of the original chords. Let me take one from this first triangle. I'll take AE from the original triangle. AE, and who does AE first and third position correspond with? And you'd have to say DE. AE is the DE. Now I want to come back to this triangle and I want to take one of these lengths. BE is in this triangle. Let me put a BE right there. And who does BE correspond with? In second and third position, it's got to go with CE, doesn't it? And if you're believing me that these triangles must be similar because those angles are congruent, then you must believe that these sides would be in proportion. And watch what happens. The interesting products that will be truthful here. AE times, let's do the product of the extremes. AE times CE is equal to DE, the product of the means, times BE. I'm going to draw the picture again because I don't want anybody to be confused by all those triangles. Here's just what I want you to remember from this. When this was A, B, C, and D, all intersecting at E. Watch the magical thing that happens. AE, this little part, times CE, this part, the product of those two lengths will equal DE, this piece, times BE, that piece. Part times part will equal part times part. That's kind of a marvelous thing. We'll set up some problems and practice that right away. Let's look at this next setup though. Consider circle X, and I guess this is circle X. I don't really care about the center of it though. I got these couple of secants, AC and AE. Introduce segments BE and DC. We're going to introduce those segments because they're going to give us some similar triangles. It says for me to get DC, and I'll put that one there. And also segment BE. And apparently we ought to have some similar triangles here. I think we do. What angles must be congruent? How about this angle at C? Has it got to be congruent to somebody? Yeah. It's got to be congruent to this angle at E, doesn't it? And thinking about this triangle right now, being similar to the other one, they both have angle A in them. Angle A is congruent to itself. I see two angles in triangle ABE congruent to two angles in triangle ADC. Those are similar triangles. I'll name them carefully. I'll name the shaded one first. ADC is similar to, and ADC was the one I've shaded, the other triangle, also beginning with A first. And this obtuse angle at D in the first triangle matches this obtuse angle at B in the second. So that had to be ABE. I care about these triangles being similar. That'll allow me to write a proportion. And when I get that proportion, I'm going to get some links that have to happen. And these are the links I care about right here. Just going to work with those. I don't really want to draw all those triangles every time. I'm just going to go back over it when I finish this setup, just to reinforce what's going on here. Okay, we're going to take a side out of the first triangle. Let's say if I took AC out of the first triangle. AC from this triangle corresponds with AE in the second. Come back to the first triangle and take another one of these segments, and that could be AD. And who does AD correspond with? It's got to be AB. These triangles are clearly similar. That's by angle. And if those triangles are similar, this proportion must be valid. And then look at the interesting products that must be equal. The product of the means, AE times AD, is equal to the product of the extremes, AC times AB. Now, let me just go back over that with you. Here's the stuff I want you to remember. I'm going to go around thinking, for this pair of products right here, the exterior part times the full length, AD times AE, is equal to the exterior part times the full length again. I guess you could have said the full length times the exterior part, but I like to think the exterior part, AB, times the full length AC, is equal to the exterior part, AD, times the full length AE. Bear that thought in mind. And look, sorry about the sound here, but we've got another one we get to look at. Consider this figure with a tangent AT and a secant AC. There'll be some products here as well. Introduce BT and TC. Let's do that. They're probably going to get some similar triangles out of that. First we have to find some angles that have to be congruent. I want to reinforce what it began with here. So let me just show the original sketch again. A, T, B, and C. Let's look for congruent angles here. Isn't it true that this angle at C, how would you measure it? On behalf of arc TB, must be congruent to this angle at T. I know that this angle is 1/2 of the arc that it cuts TB, and so is angle C, half of arc TB. And I'm really thinking this small triangle is similar to the large triangle. They both have angle A in them. Angle A matches itself, so angle A and angle C are congruent to angle A and angle T. So I got two angles in that shaded triangle congruent to two angles in the large triangle. I got similar triangles there. I'm going to have to name them with care. ATB is similar to A started with A, and that angle matches itself. The angle at T in the first triangle, ATB, matches the angle at C. So that would have been angle ACT. Those are similar by angle. And then we're going to write a proportion. And look, I only got 3 things to use. This is going to make it more interesting still, isn't it? Okay, let's take a side amongst these sides, amongst these segments. That's in this first triangle. That could be AT, huh? AT in this triangle corresponds with AC in that one. Come back to this first triangle. What about AB? That's one of the things I care about. And who does AB go with? Well, AB corresponds with AT again, huh? I kind of like this one the best of all of these. What pair of products must be equal? Well, the product of the extremes is the interesting one, huh? AT squared is equal to the exterior part AB times the full length AC. These are the big things you want to recall from here. You don't want to draw those triangles every time. You just want to remember how this worked. And what I would want you to remember here is the tangent squared is equal to the exterior part times the full length of the secant. Now I'm going to set up a few problems where we can practice with those kind of things, and then you have an assignment like that to do as well. So here's a question. Got a couple of chords intersecting inside a circle. AC intersects DB at point X. I'll tell you right up that AX is equal to 6 and XC is equal to 12. Well, XB is equal to 9. I know I've got similar triangles here, but I don't really want to go back over that. I just want to remember those products that must be equal. And in fact, it was part times part. AX times XC is equal to part times part BX times XD. That's what's going to work here. So, in this case, it's really going to be 6 times 12 is equal to 9 times dx. And that works out pretty cleanly. We got 72 here is equal to 9 times dx. We'll divide both sides by 9. dx would have had to have been 8 in that circumstance. I think in a minute I'm going to draw a couple of careful circles and measure them really carefully. We'll see that they work out cleanly. Let's try another one. Let me set one up for you. Get a look at this sketch with a couple of secants. I'll tell you ahead of time that AC and AE are secant of this circle. AB is 12, and BC is 8.
Powering off.
AD is 16. Find length of DE. I know there are similar triangles here, but that's not what I want to deal with right now. What I'm going to remember is the exterior part times the full length is equal to the exterior part times the full length. So, in that case, that would mean that exterior part 12 times that full length, 12 plus 8, going to be able to be 20 right there, huh? Must equal the exterior part 16 times that full length. And that have to be 16 plus DE, I'll call it X for right now, plus this amount X. And so I got 240 is equal to, ooh, I got a problem here, 256, huh? And this couldn't happen, could it? So I'm going to write a better question for you, because as soon as I got that 256 plus 16X, that's going to require this to be negative. So I've just discovered I set up a problem here that could not be solved. So I just adapted that then. Instead of letting this length be 16, I'll let it be 14. I think I'll figure out how to make it now. I think that was just too big a length. It couldn't happen that way. But here, same kind of idea. The exterior part 12 is to that full length 20. As the exterior part 14 is to that full length 14 plus X. And we're going to get a funny answer out of this, it seems like. I get 240 here is equal to 196 plus 14X. Got to subtract 196 from both sides. I guess that'll leave me with 44 is equal to 14X. Divide both sides by 14. I'm not going to get a whole number, but that's okay. X would be, I guess that's about 22/7. So that would be 3 1/7. That's what that length would have had to have been. Let me make up another one. So here I've got a tangent and a secant to a circle, and I'm given some lengths. The exterior part of that secant is 8, and the interior part is 12. And I want to find the length of that tangent. I know there's similar triangles here, but what I really want to remember is the tangent squared is equal to the exterior part 8 times the full length 20. That's all I got to solve is that little trick right there. So AT squared is going to equal 160. Take the square root of both sides, and AT itself, well, what do you know about that? Well, it is 16 times 10, huh? So I have to call that 4 times the square root of 10. Now, let's do that with some actual measurements and see how that goes. So I've just drawn a couple of chords that intersect each other, let's say point P. And I'm going to measure these as carefully as I can, and we're going to check it out and show you that the darn thing really does work that way. So let's figure out how long those chords, those parts of those chords are. And I'm just going to start at the 200 and measure it right there and say that's about 62 millimeters there. And what about this other part? I'll start at the 200 again and say that that's about 60, I guess 67 there. And I'll tell you what, let me measure this small part right there. From 200 to the up 41 millimeters there, as close as I can get. So I ask you, how long should this be? Let's figure that out, then we'll measure it in a second, see if it works out like it should. So with those measurements, I want to figure out how long dP is. So, and I know that it's part times part equals part times part, so I just think it ought to be 62 times 67 equals 41 times dP. And I got my calculator for that, so let's just see how that runs. With 62 times 67, give me 4154, equaling 41 times dP. I'll divide both sides by 41, and it's going to be about 100, isn't it? Let's see what I got to get out of that. 4154 divided by 41. So we ought to get about 101.3. That's how long this length should be. And let me give you a good look at that. I'm going to start at the 200 and check it out. And it's not perfect, but it's pretty darn close, huh? From 200 to 300 is about a little tiny bit more than 100. So I'm going to take that. Yep, that worked out pretty good. That should have been about 101.3. Huh? Let's do that again. I'm going to do it with a tangent and a secant, I think, though. So I drew a couple of secants and a tangent to this circle. Kind of hard to get everything just right. We'll see how it comes out. This exterior part is about 5.1 centimeters and the interior part is 8.7. This exterior part, best I could measure it, was right at 4 centimeters. Pretty darn close, right at 4 centimeters. And I want to figure out this interior part here. And I want to figure out the length of this tangent segment as well. What we got to remember is this exterior part, 5.1, times that full length, 5.1 plus 8.7. Ought to equal that exterior part 4. Times that full length, 4 plus BC. There's more clever ways we could have gone about this, but let me just charge through it with what I got. 5.1 plus 8.7. I do that in my head, I'm sure, but I'm going to get it right every time this way with my calculator. At least I think I will. So 5.1 plus 8.7, giving me 13.8. Multiply that times 5.1. So on the left-hand side, I got 70.38. Should equal 4 times 4 plus BC. I'll divide those sides by 4. I'll be left with 4 plus BC here. I'm sure there's a more clever way to handle this, but just take that 70.38 divided by 4. And I got 17.595, about 17.6, let me say. Subtract 4 from that, and I guess BC would have to be whatever 17.6 minus 4 is. We'll go for about 13.6, huh? Now let me just measure that length. I hope that this length is about 13.6. Measuring as carefully as I could, I can only go to 10, but let me just make that movement. There's 10 centimeters right there, so I want this last to be 3.6. And I think it is pretty darn close, huh? It's not perfect, but it's about 3.6, and my measurements aren't great. So I think that worked okay. So what about that tangent segment? How long should it be? And what I should remember is the exterior part times the full length is equal to the tangent squared. So that 5.1 times that full length, 13.8, ought to equal the tangent squared. I'll call it TA squared. Let me just see about that then. I'll do it with my calculator. And we just see if it works. It won't be perfect, but it'll be pretty darn close. 5.1 times 13.8. Give me that. And let's figure out what the square root of that is. So I'm looking for about 8.4. Now, the subject of interpretation, where is the point of tangency? Well, I tell you, it's 8.4 centimeters away. We'll see if that looks pretty good. 8.4 says that the point of tangency should have been right about there, huh? Yeah, I'm taking that to be right at 8.4. So I'm thinking this stuff works.